Page 387, Statistical Control Charts. One of the most common variable control charts is the X-bar chart in combination with an R chart. Let's go directly to an Excel file and see what this looks like. This Excel file is named SPC Charts, and the worksheet is named X-bar and R chart. Here we see an X-bar chart on the top. Here is an R-bar chart below it. In the middle is a set of data that is plotted on these two charts. In the upper X-bar chart, we're plotting the iron concentration in HCl each day for 31 days. That's the blue line with the black markers. And each point on each day actually represents the average of 5 samples per day. For the first day, the average is 10.6 ppm. Here's that point. On day 2, the average for the day is 11.0 ppm. Here's that point, and so on. So this is the iron concentration average each day for 31 days. The central black line is the average of all 31 days. It's the monthly average. It's the average of all the daily averages. It's called X-bar and it's 10.6 in this example. The upper dashed line represents X-bar plus 3 standard deviations above the mean. And the lower dashed line represents X-bar minus 3 standard deviations below the mean, based on the standard deviation of the process. Now, if you recall your basic statistics and the normal distribution, the odds of a point falling outside plus or minus 3 standard deviations, if only common cause random variation is occurring, the odds are really small. Only 0.3% of the time, because 99.7% of the time, randomly varying data will fall within plus or minus 3 standard deviations. So it's only 3 times in 1,000 that any random point would fall outside the upper and lower control limits. That would be a cause for action by the operator of the process. As long as the data falls within plus or minus 3 standard deviations, then the process is likely operating randomly, that is properly. There are more considerations to look at, and we'll do that later, but we're going to create the chart first. Below the data I have what's called an R-bar chart. So the R is the range. It's the range of the daily data, max minus the min of the 5 values. And for day 1, that's 2.1. The range max minus min for the second day is 1.7, and here's that point plotted, and so on all the way across. Now the black central line is the average of all the daily ranges, and that's called R bar. A bar means average. The upper dashed line represents R bar plus 3 standard deviations of the ranges. Range charts give different information than X-bar charts. Any point that falls outside the upper and lower control limits on an X-bar chart indicates special cause or bias is present in a process. But range charts don't detect bias or special cause. Range charts measure the difference between readings on a given day. So they measure the amount of precision or the variation that's taking place in a process. If a process is running very stably, then the range would be small and the average range would be very low. That would be ideal. There certainly is a lot more to be said about interpreting control charts, but that's a discussion for a later course in the program. In this course, I want to take you through the process of creating an X-bar and R chart, and in fact generating the data to do so. Here's the spreadsheet that you'll be given to work with. Our first step is to generate a set of random data, 31 days, 5 samples a day, that are randomly generated, and we'll set constraints between 9 and 12 ppm of iron. To do this, in cell D24, the top left corner of the range of samples, we'll type in a formula to generate a random number between 9 and 12. This will be equal to 9 plus a random number generator, rand between 0, 30, close bracket, times 0.1. So this will generate a number, a random number between 0 and 30 times 0.1 makes it a number between 0 and 3 added to 9. So the number will be anywhere between 9 and 12. Now you can drag that formula down for 5 samples in a given day. And then we'll drag all 5 of those across for 31 days. Because the numbers are randomly generated, you'll notice that every time we hit enter on this worksheet, the numbers will be randomly regenerated, and so the numbers will change, but they'll always fit within the random constraint that we gave it. There's another random number generator function available in Excel I'd like to show you. In cell D24, let's try this, equals 9 plus, this time we'll just write rand tab, and we'll just close the brackets, times 3. So we'll have 9 plus a random number times 3. When you don't give this function an argument, it generates a number between 0 and 1, and that'll be multiplied by 3. That will also give us a number randomly distributed between 9 and 12. Notice how all the values changed when I pressed enter. Now we'd like to get the sum of 5 samples for the day. I'm putting my cursor in cell D29. You could type the formula equals sum. There's a shortcut here on the formulas tab under auto sum, and click sum, and it automatically adds up the values above it. And notice it's including the 1. We don't really want that, so let's drag down to exclude it. Now we have the range we need and press enter. Now with relative referencing, we can simply drag this formula across for all 31 days. Now for our purposes, we don't really need the sum. We simply want the average. Understand that in industry, it's commonly done this way. So workers on the shop floor, they may not be measuring iron concentration, they might be measuring the size of a part. They would take X numbers of readings a day, add them up, and then divide by the number of readings to determine the average. But in Excel, we have functions that do it automatically. I just put it here for sake of completion, and it often is the way it's used in industry. What we really want is the average. We can use the average function for that of the 5 samples for the day. 10.3 looks like the average. We can drag that cell all the way across with the autofill button. And now we have every day's average. What we now want is the average for the whole month, the average of the daily averages. That'll be equal to the average of all 31 days. Now this time you want to add an absolute reference, so F4. And the reason for that is we want to drag this formula across, but we don't want it to change. The average has to always refer to the same 31 columns of data. So we should see the same number all the way across. Notice it recalculates every time, but at this point in time, our average for the month is 10.7. Now before we can get the upper and lower control limits on the X-bar chart, we'll need to get the range values. And the range will be equal to the maximum minus the minimum for a given day. That's equals max of the 5 samples in the day minus the min of the same 5 samples. So the range for day 1 is 2.1, and we can drag that formula across for 31 days. Now we want to get the average range for the whole 31 days. That'll be equal to the average of all 31 daily ranges. Make sure to hit F4 because we need an absolute reference. And that's because we want to drag this point across, the average for the month has to be a singular value. Currently it's at 2.1. All right, to get the upper and lower control limits, recall that it's x bar plus 3 standard deviations or minus 3 standard deviations of the mean. In industry, rather than calculating x bar plus 3 standard deviations, it's more commonly calculated as x bar plus a factor from a statistical table times the average range. And this gives the equivalent of x bar plus 3 standard deviations. And we'll talk more about why this is used and even the advantages of it in a later course. But for the time being, if you could just accept that this is an alternate way to calculate the upper control limit, we can do that here. So the value of A2 depends upon the number of samples that are averaged. When 5 samples are averaged, A2 is 0.577. It's multiplied by R bar and added to X bar to give us the upper control limit. So in this cell, which is D32, we'll type the formula equals X bar, relative reference is fine, plus A2. Now I could select it here and that's fine, but just for sake of clarity, I'm going to type it in 0.577. Again, that's A2 for a sample size of 5 times R bar, which is 2.1 in cell D35. We only need relative references because notice X bar and R bar are constant all the way along. Our value is 11.7 currently, and let's drag across and get that for all 31 days. It should be a constant value. The lower control limit on the X bar chart is calculated as X bar minus A2 times R bar. So that'll be equals X bar, that's cell D31, minus A2, which is 0.577 times R bar. That is cell D35. We don't need any absolute references. It should be consistent as we drag across. Currently it's at 9.5. Lower control limit at 9.5, upper control limit at 11.5, X bar at 10.5 looks about right. We'll also need to get the upper control limit on the R bar chart. Now for that, we could calculate it as R bar plus 3 standard deviations, but in industry it's more commonly calculated by this formula, D4 times R bar. And D4 is taken from a statistical table, depends upon the sample size, 5 in this case. So we'll use the value 2.114. That'll be equal to 2.114 times R bar. I could use a cell reference here, but I wanted to make it clear exactly what I'm doing for the formula. We don't need an absolute reference. It'll be the same across. And that looks consistent. All right, so we're ready to plot our graph. We'll start by plotting the daily average values. Let's select the data in row 30. Control C copies to the clipboard. See the flashing marquee indicates that's active. Now go to Insert. We want to insert a line chart. 2D line chart. Don't choose stacked lines. It won't work out properly. Just choose line chart. So there's our daily average being plotted. Before we do anything else, let's choose the format for it. With the chart selected, Chart Design tab, Quick Layout number 1 gives us placeholders for the axis title and the chart title. Really don't need the legend. The y-axis title will be equal to iron, and that's ppm. The chart title will be iron in HCl, and this is called an X bar chart. Right, so now we should drag this such that the days on the chart align with the days in the table. Makes it easier to read. Yes, that's not bad. So let's add major grid lines. Right click on the x-axis, add major grid lines, helps us line it up. Notice how the point that's plotted is in the center of each cell, and that's easy to read. Next, we want to add X bar itself. To get rid of these flashing marquees, just hit the escape key. Let's select the X bar values all the way along for all the days. Control C copies to the clipboard. Select the chart so Excel knows where you want to paste it. Go to the Home tab, Paste Special. Notice that we're adding new series, which is correct. The data is in rows, and that's all you should check off. Anything else gives some messed up version, and say OK. And there's our X bar line. And we'll fix the colors and the size in a bit. Escape to get rid of the flashing marquee. Let's plot the upper control limit on the X bar chart. Select all 31 days of data. Control C. Select the chart so that Excel knows where to paste it. Home, Paste, Special, and OK. There's the upper control limit on the X bar chart. Escape to get rid of the marquees. Let's select the lower control limit on the X bar chart. All 31 days. Control C. Select the chart. Home, Paste, Special, and OK. Lower control limit. Looking pretty good. All right, let's change the range of the y-axis so we can fill our chart with data. I'm going to take the minimum value as 9 and the maximum as 12. I'll right-click on the y-axis and format the axis. I'll choose a minimum value of 9 and a maximum of 12. That looks better. All right, now let's fix up the presentation of this. The X bar line is typically a solid black line. If I right-click on the line and choose to format the data series, then choose this Fill and Line Options button. We want the line to be a solid line, and then we can set the color to black. Well, there it is for us. And that's done. Now the upper and lower control limits, we'd like to have dashed red lines. Right-click on the upper control limit line, format the data series. In the Fill and Line option button, line should be solid. Here we'll choose dashed, and we'll choose a color of red is typically used. It's a warning line. And likewise on the lower control limit line, format the data series, Fill and Line, solid line, red and dashed, and OK. We normally show dots each day on our average plot. So right-click on that line, format the data series, the Fill and Line group, and we want to select here markers. Choose Marker Options, Built In, and we'll choose black for a fill color and say OK. That's looking pretty good. This is a good plot of an X bar chart. Now, something very interesting you see here. There is one point on day 30 that falls below the lower control limit. Now this number was randomly generated, and it can occur, what's the probability? 3 times in 1,000 that this data point happens to fall below the lower control limit. But that's the reality. 3 times in 1,000 it will. All right, let's create the R bar chart in similar fashion. I'll hit Escape to get rid of the marquee. Select the daily range values, all 31 of them. Insert a line chart. This usually sits below the data, while the X bar chart sits above. With the chart selected, go to Chart Design, Quick Layout 1. The y-axis title on this one, FE daily range, and that's ppm. This is called iron in HCl R bar chart. We don't need the legend. Let's make this line up with the days of data. Pretty close. Right click on the x-axis, we'll add major grid lines. Alright, so typically you want to be able to look at the chart and the data at the same time. Looks like it's pretty well lined up. Well, I'll go through it again and you can fast forward this if you already know how to do this. We'll want to add the R bar line. Select the values, Control C, select the chart, home, paste, special, new series in rows, OK. There's the R bar line. We want only the upper control limit line. I'll hit escape first. I will select the upper R bar data, Control C, select the chart, home, paste, special, OK. All right, let's tidy it up. The upper control limit line, right click on it, format the data series, line and fill. The line, we want a solid line, we want it dashed, we want it red, there it is. The R bar line, let's right click on that, format the data series, line and fill, we want a solid line, and this one should be black. And then our actual data plot, we'd like to have markers for each day. Right click, format the data series, line and fill, choose the marker group here. We'll choose marker options, built in, and we'll make the color something distinctive, in this case black. There's our R bar chart. Looks quite normal. So there we have an X bar and R chart as done in industry. Now many times in industry, a company will purchase software that creates X bar and R charts directly, and this is practiced throughout the entire industry, in the process, in the lab, in the sales department, in shipping and receiving, in the maintenance department. There's charts upon charts upon charts if the process is properly monitored. But in the lab, you can create charts using Excel now for any purpose that you decide something is worth being charted. A lot more to say about this later. Let's briefly go back to the notes and I'll point a few things out to you. Page 390. Let's briefly talk about how to interpret control charts. It would be a shame to come this far and not discuss it to some extent. Some charts have lines dividing 1, 2, and 3 standard deviations. The region between the mean and 1 standard deviation is called zone C. Between 1 standard deviation and 2 is called zone B. Between 2 standard deviations and 3 standard deviations is zone A. As you might imagine, more points will fall in zone C because they're closer to the mean. At least they should be falling more in zone C than in zone A, for example. All right, what are some patterns that suggest a problem with a chart? Well, here's a few examples. Assign a number when a point falls in a given zone. So a number of 1 for any point falling in zone C, a number of 2 for any point falling in zone B, and a value of 3 for any point falling in zone A. And what you do is simply add the values up. When the chart crosses the mean, then you re-zero your count and start again. Here is 1, then we cross the mean, that goes back to 0. Here is 1, crosses the mean and goes back to 0. Start counting again. Here's 2, plus 1 is 3, plus 2 is 5, plus 6 is 1, plus 1 is 7, and it's circled. So the rule is investigate when the sum reaches 7 or more. The reason being, this is unlikely if the data is normally distributed. This would imply that some special cause is occurring in the process that's biasing the numbers. That's one indication of a process that's out of control. Here's another example. Anytime 7 or more consecutive points are on the same side of the mean, 1, 2, 3, 4, 5, 6, 7, 8, there's a problem here. This is not normally distributed. Something is biasing the process. Time to investigate. 7 or more points consecutively increasing or decreasing. 1, 2, 3, 4, 5, 6, 7, 8. That's not normal. Points should be randomly moving up and down. Something is trending the process downwards. This might be tool wear if you're making parts. Maybe a cutting device is wearing out as parts are getting smaller, for example. If this value represents a concentration, for some reason the concentration is continually falling. Maybe you're diluting the sample too much. Maybe it's not being distilled long enough. Something is amiss in the process. There are other out-of-control indicators. Any point that's beyond the control limits, already mentioned, only happens 3 times in 1,000, should automatically be investigated. Any 2 out of 3 points beyond 2 sigma is quite unlikely. Now, a single point falling in this range, zone A, is not a big concern. That happens 5% of the time. But 2 out of 3, that's quite unlikely. Time to investigate. 14 consecutive points alternating up and down. That's something you might miss, but really they shouldn't all be continually oscillating. Something's causing the process to cycle. And then any other non-random pattern. When the process is out of control, investigate, find the special cause of variation and remedy it. When the chart is okay, do nothing. So again, there's more to be said about this in a later course, but that's a good intro for now. Page 392. A couple more QC tools that Excel will generate for us. Histograms and Pareto charts. These are used in industry commonly to evaluate a supplier's performance or the company's own performance. Let's look at a typical example. A chemical company shipped 100 rail cars of HF during the month of July. The water analysis of each shipment is given in the table below. These are not dated, they're just a collection of data. We'll use one of Excel's random number generators to generate 10 columns of 10 values, a matrix of 100 values. Then we'll want to plot this in a histogram. Take a look at the next page. This is a histogram. It's also called a frequency distribution. So over the range of, say, 11 to 20 ppm, how many samples were in that range? In the range of 21 to 30, how many samples fell in that range? From 31 to 40, how many samples fell in that range? So it tells the relative frequency of various results. If this is normally distributed, and it approximately is, then we can conclude that the data is normally distributed and the process is in control. If it's not symmetrical and normally distributed, we can then conclude that there's some special cause of variation that needs to be investigated and eliminated before we can do much more. Before we generate the histogram, let's go ahead and generate the 10 by 10 matrix of data, and then we'll show you how to create the histogram. Let's go to an Excel spreadsheet for this. This Excel file is entitled SPC Charts, and the worksheet is called Histogram. And I've identified 10 columns and 10 rows where we'll generate 100 values randomly. Let's start with that. On the Data tab, choose Data Analysis and find Random Number Generation. Say OK. Now the number of variables means the number of columns. Choose 10. And the number of random numbers means the number of values per column, and that'll be 10. That'll give us a 10 by 10 matrix. Now the distribution of the data, we'd like it to be normal. You can choose from a number, but we're looking for a normal distribution. Let's choose an average or mean of 50 and a standard deviation of 15. The random seed is not needed. It simply means that it will give the same starting value for each random number calculation. We're not concerned with that in this case. The output range is the cell in the top left corner of the numbers to be generated. And then say OK. There are 100 values with a mean of 50, standard deviation of 15, randomly varying. Now we don't need decimal points. We're measuring ppm, and so typically we don't have decimal points. Let's get rid of those. The nearest 1 ppm should be sufficient. So I'll explain in a minute why you'll want the minimum and the maximum and the number of values. So to get the minimum function, just type equals min and select the range of the data, all of it, and enter. To get the maximum, do it the same way, equals max and select the range of data. Likewise for the count. Let's go back to the notes for a minute. Before we can create the histogram, we should determine the number of intervals and the ranges before using the histogram tool. If we don't specify the number of intervals and the ranges, Excel will use a number of intervals approximately equal to the square root of the number of values in the data set, with equal width intervals starting and ending at the minimum and maximum values in the data set. Our minimum was 18 and maximum was 85. We're going to wind up with interval ranges in decimal values like 7.246 and 15.475. Not very useful. By specifying the number of intervals ourselves and the ranges, we can use numbers that are simple multiples, multiples of 2 or 5 or 10, which are much easier to analyze. So here is explained how to obtain the min and max in the count, which we already know. Now our minimum was 18, our maximum was 85. We can use these extreme values to help us determine the limits of the histogram intervals. Usually 5 to 15 intervals are used in a histogram. We'll use 10 intervals of 10 ppm ranges. So let's go from 1 to 10, 11 to 20, 21 to 30, and so on up to 91 to 100. Now Excel refers to the maximum value in each interval as a bin. So the bins are 10, 20, 30, and so on, up to 100. Since the second bin is 20, then the second interval will include all the values greater than 10, the previous bin, up to and including 20. Then the histogram tool automatically adds an extra interval labeled more to the bins that you specify. Now our last bin will be 100, and then any values that might exceed 100 would fall into the more bin. Let's go back to the spreadsheet and I'll show you how this is done. We're still in the Excel file named SPC Charts. We're still on the worksheet entitled Histogram. In cell A5, type in the label bin. And below that, we're going to list our bin values starting at 10, then 20. That should be enough for Excel to pick up on the pattern. Drag that down to 100. On the Data tab, choose Data Analysis. This time choose Histogram. OK. Now the input range will be all of the data, all 100 points we want analyzed. The bin range, choose all 10 bin values plus the label bin and make sure you check off a label. For output options or output range, select cell B5. Don't overwrite the existing one, it'll mess it up, but put it right beside the existing set of bin values, so B5. We want to check off chart output. We can also check off cumulative percentage, and for now we'll leave Pareto chart unselected. We'll look at that later. And simply say OK. Overwrite some of the data? OK. I don't see what was overwritten, no problem here. So it recopied our bin values. If we had tried putting it on top, it would mess up the chart, but this is fine. This is the frequency of the values that fall between 0 and 10. This is the frequency of the values that fall between 11 and 20, between 21 and 30, and so on. Then we have a cumulative distribution here. Let's tidy this up a bit. And here's our histogram. Our histogram shows the number of values that fall within each bin range, as indicated in our table. The red line is the cumulative percentage. This can be useful, as you'll see, when you're trying to find a value that represents the midpoint, for example. We won't say more about it in this application. Now, normally histograms are presented without gaps. If you right-click on one of these bars, go to Format the Data Series, we see our gap width is 150%. I'm going to reduce that to 0. We need to add some borders to this to make it more discernible. Under Fill and Line, here's Border, Solid Line, black is fine. We can choose to increase the line width a bit. There we go. Now it's easy to read, and that's typically how they're presented. So what's this telling us? If I didn't know the data was randomly generated, looking at this histogram, I would doubt that in fact the data is normally distributed. But that's the nature of random number generation. Occasionally it happens that it doesn't look that normal. If we do this a second or third time, I suspect you'll find it more normal looking in most cases. The point here is don't be too rigorous or too strict in interpreting a histogram. Realize that random numbers vary randomly. There's a histogram. It's one of the first steps in evaluating process data using QC methods. Page 395, Pareto Charts. Pareto charts are similar to histograms, except that the intervals are sorted and presented in order of decreasing frequency. This is most often used when a company is trying to identify the most commonly occurring or perhaps the most costly problem in a process. Once identified, the worst problems are tackled first. Let's go back to our Excel file and create a Pareto chart, and I'll explain more about them. We'll use the existing data and create a Pareto chart. Select the bin label and the bin values, and we'll just drag a copy of that a little further down in the chart. How about A20 through A30? Choose the Data tab, Data Analysis. I want histogram again. Say OK. This time unselect cumulative percentage, but check off Pareto chart and chart output. Now the input range will be the same 100 values that we chose previously. The bin range will be our new bin range, including the label. Make sure label is selected. For the output, select the top left corner of the data output. That'll be cell B20. Pareto chart and chart output, and say OK. I think we can dispense with the legend. It's pretty obvious what this is. There's our sorted histogram, which is called a Pareto chart. Now typically there's no gaps between the bars. If we right click on one of the bars and choose to format the data series, let's eliminate the gap width. On the fill and line group, we want a border, a solid line, black is fine. Let's increase the width so it's more visible. Alright, so there's a Pareto chart. We can make these a little more attractive or interesting if we make it a 3D chart. So just right click on the chart area and choose to change the chart type. And let's choose a 3D column chart This one looks good, and say OK. Now we can change the rotation of this 3D chart. Right click and choose 3D rotation. Notice we can rotate on the x-axis, y rotation, and so on. Let's see what perspective does. We can exaggerate it a bit. So that's how to create a Pareto chart. Let's take a more realistic example. At work, in our quality team, we had members of the maintenance department, the operators, the lab foremen, the managers, and together we would brainstorm and come up with the reasons why the product might have been off spec on certain days. We listed these, and we have the frequency. Equipment failure was identified 5 times being the cause of product off spec. The purity of the feed. The instrument problem was identified twice. A lab error was identified 4 times. Power failure 3 times. The distillation rate is too high, 6 times. 8 other times we don't know why it was off spec. Let's create a Pareto chart to prioritize what we need to work on first. We'll first need to sort our data. I won't use the histogram tool. I don't think it can be applied directly here, but we can certainly create a histogram manually in Excel. So let's select all of the data, including the labels, and on the Home tab, choose Sort and Filter. We'll choose Custom Sort. Now, because I've selected the headers or labels, make sure you check off My Data Has Headers, so this is not considered as part of the data. We'll sort by the frequency, which is this column here. We want it to be from highest to lowest, largest to smallest, and say OK. So the data has been sorted. Now we can create the Pareto chart. All right, let's select the data to be plotted. Leave out the labels this time. On the Insert tab, choose Column or Bar Chart. And let's choose a 3D column chart. That looks pretty good right there. Let's get rid of the legend. On the Add Chart Elements icon, we can choose Axis Titles. All right, there's a placeholder for it. We'll type in frequency. This will be cause of off-spec product. Here's our causes listed in order of decreasing occurrence. Gap width, let's try a little less here. See how that looks? Looks pretty good. And this will be cause. All right, so our quality team can now look at this and decide what are we going to work on first. Well, we can't so much work on unknown, or maybe we could identify it. How about the feed purity? How about the distillation rate is too high? Let's consider these factors first. So there's a Pareto chart. It's simply a sorted histogram. It's used in QC management for industrial processes.